Hello. Hello, hello, hello. Yeah, yes? Okay. All right, so welcome back to DSP. And let me remind you that next week will be holiday time, so there will be no class meeting the entire week. Next week we will not meet, but then the week after that, it will be our first midterm. And the coverage will be from the beginning of the semester until today's material. So today I believe we can finish this lecture. So your midterm will cover from lecture 1 to lecture 6. Okay, yeah. Any question regarding the midterm? And tomorrow we have I gave you last year's first midterm, so you can take a look and see kind of the level of difficulty, 难度大概到哪边，level of difficulty should be around about the same, but the questions will not be the same. Right? The level will be about the same. But anyway, so today we continue to study this quite important topic, linear difference equations. And we emphasize that the coefficients we are using there are all constant, okay? Time invariant coefficients. So linear difference equations, as we see them, they give us an implementation of a causal linear system, which is time invariant, so it's LTI, linear and time invariant, okay? And so in this course, in my class, I focus on using linear difference equations in a causal manner, causally. So remember the definition of causal system, it's about the impulse response, right? The impulse response should be all zero before time zero. Nothing will happen before the system receives any input, okay? So we limit our focus to the usage of linear difference equations in a causal manner. So last time we spent a bit of about 10 minutes. We went through this definition. So let's take a look again. So this is an equation with yn on the left-hand side, right? And on the right, we have linear combination of y, the output, the past samples, 过去的一些 sample, past samples n minus k, right? So from the previous sample all the way to the nth previous sample. We have a linear combination here, and the linear combination coefficients are all constant. The A and B, these coefficients are also constants. Okay, so take a look. That's the definition with yn on the left-hand side and everything else on the right-hand side. So you can also see this as one line of computer code. Seriously. Yeah, you can view this as one line of computer code, and this system can be implemented. 它可以被实现, or the system can be implemented. But otherwise, it's a rather straightforward definition. Everything's linear here. So just take a quick Z transform. So if we take Z transform on both sides of the equation, then this is what we have. Okay, not exactly this, but then Y should become big Y, right? Z transform. Y becomes big Y. X becomes big X. And we also apply a simple property that when we delay, if xn corresponds to big X of Z, then xn minus 1 as a signal which relates to n by shifting to the right with one sample. If we shift in the time domain by one sample, then the Z domain is rather simple to check that the Z transform becomes, there's an extra factor right here multiplied by big X. Okay, so if you apply this property to both sides, here we have the delay by k samples, right? Delay and k equals to 1 to big M, k, yeah. So you can just figure out that on the left, we will have Y of Z equals to something like summation minus a k, Z to the minus kth power, and the k index remains the same with this limit from 1 to m. So that is a polynomial. That looks like a polynomial. So on the right, we have this term plus this other next term. Again, with summing from 0 to big N, according to my notation. And bk, now delay is replaced by z to the minus k power. That's a factor that will appear right here. And xz, right? And the next thing here is to move everything that relates to yz, that has yz, move everything to the left. Then we have yz times a polynomial a of z equals to x of z times a polynomial. If we define this as a polynomial, if we define this as b of z, and it is in here we have a polynomial 多项式啊, we have a polynomial of z to the 1 over z, basically 一除以 z, z, or I say z inverse, z 的导数啊, z inverse 啊, z to the minus 1. Yeah, so we will stick to this notation in the entire semester and also in MATLAB. Okay, in the official documents of MATLAB, we stick to this notation. Ya equals to xb. It shows up a lot. We'll be repeatedly seeing this equation. Okay, so it will be nice to become familiar with this equation. Okay, yeah, please be familiar. Familiarize yourself with this equation, Ya equals to xb. Or we say yz divided by xz. Yz divided by xz equals to a go here, b goes on the top. Okay, bz divided by az, where both of them are polynomials of z inverse. So far, so good? But remember that y, what is y? Y is the output of our system, the output that our system produces while receiving the input x, right? And this is an LTI. Okay, so yz divided by xz is exactly the z transform of the impulse response, which is denoted as big H. Because we're talking about this, obviously this is a linear and time invariant system. Okay, yeah. So far, yeah, that's what this equation, this chain of 3 equalities are defined in this manner. Ya equals to xb, therefore y divided by x, which happens to be the system function, big H, should be equal to b divided by a, where both of them are polynomials. Okay, so far so good? So this is just in the z transform domain, we immediately have this consequence. So with that, kind of a key question we can ask. First, given the coefficients, given these a and b coefficients, is there a way to calculate the impulse response given any such kind of difference equation? And the answer, of course, there is. Right? Okay, I will see how to do that. But then the next question is also important. When we write down any difference equation, sure, then we'll see a moment that we can calculate the impulse response. But there's a general design rule, I say, 是一个设计上的原则 design principle, that when we design a difference equation in DSP, most of the time, in most applications, you want the system to be stable. We don't want the system to receive an input and the output goes to overflow. Okay, the output explodes to 10 to the 306 power. So we don't want that to happen, right? We don't like that. Yeah, we do not like that. So we want the system to be stable in a way, in the sense that when the system receives a finite input signal, or we say BIBO, when the input is bounded, the output should also be bounded. Some of you might be able to recall that this is probably something that you have learned in signals and systems. Yeah. As a general design principle, we don't want our system to be unstable. Okay? So to ensure that the system is stable, let's jump to the conclusion that we'll see that we need to check a property of A of z. Okay, consider A of z being a polynomial, so it has roots, right? A of z is a polynomial of mth order, mj 的多项式嘛. So in principle, it has m roots, right? And we require all the roots to be inside the unit circle. That's the conclusion. Okay, that's the conclusion. We want all the roots of A of z to be inside the unit circle so as to ensure that the system will be stable. Okay, and there's a reason we'll cover. These are the topics that we'll cover today. First of all, let's learn how to calculate the impulse response of any difference equation systematically. And second question is understand. We want to understand why this is case. It's all about A of z. Okay, no requirement whatsoever for B of z. Just check the roots of A of z. Okay. And it actually makes some sense. You see that here, A of z, if we go back one slide, what is A of z? A of z is kind of a feedback, producing the output, and then the past output will influence the next output, the present output. Okay? So in a sense, this is a sort of feedback. The system produces an output and we store it, and then that output will influence the next sample. Okay? So this is feedback. So when there's feedback, we worry about stability. Okay? But in here, it does not affect stability. Okay? But the coefficients here do affect stability. So that's kind of that also explains why in terms of when we analyze stability, we only check the roots for A of z. We don't worry about B of z. Okay, no worry about B of z. Okay, yeah. Anyway, so let's now the next. So those are like the general scope and formulation. We have z transform. We apply z transform to a difference equation, and now we have ya equals to xb. Okay? Any difference equation can be transformed to this equation in the z domain. Right? Okay, so in the next few slides, we will use Fibonacci sequence as an example. It turns out that Fibonacci sequence is the solution, the impulse response of a difference equation. So let's take a look. And this is the difference equation we're talking about. Okay, let y be the sum. This is a linear combination of past samples, right? Linear combination of the two samples in the past. So that's this part. That's this part. Okay, that corresponds to that part. Plus our input. Okay, simply the input itself. No linear combination. So this is a pretty simple case with all the coefficients 1, 1, and 1. Probably a very simple example, right? So then our goal is to calculate the impulse response. Yeah. So by definition, what is impulse response? Impulse response is the system's response when receiving delta function as the input, right? So just by definition, we can write, okay, if H denotes, H 用 H 来记载啊，用 H 来表达. If H denotes the impulse response, then by definition, this is what's happening when the system receives delta as our input. The response should obey this equation, the original equation, with H being the output, delta being the input, right? So when the input is delta, the output is H. Right, so far so good? So if we move one step further, then let's go to the Z domain. Going to the Z domain, we have this relation. What is H? Then H is 1 divided by that. This is B of Z, this is A of Z. Okay, so one or the other. So you can probably rather easily reach this conclusion that H of Z, in this case, can be written as B of Z divided by A of Z as a special example. Okay? So far, nothing's new, just same thing right here. Okay? So far so good? We good? Yeah? Okay, so, but then next step, I suggest let's do a factorization. 做一下因式分解啊 Factorization. Let's factorize a of z. A of z is a quadratic polynomial. 它是二次的，对不对？ Yeah. So it has an order of 2, so we expect that it should have 2 roots. They might be the same root, which is not the case right here, but in general, a of z, if the order of a is 2, then we can further factorize this polynomial into this form. And please do note that a of z, the leading coefficient, 那个首次的这个什么 leading coefficient, 常数项的那个系数 the leading coefficient is always 1 in this entire formulation. Okay? Please notice that this is so 1 minus something. This is a1 coefficient, a2 coefficient. Right? It's a second order polynomial. In principle, it should have 2 roots. And this is the way we express the factorization. Okay? And the 2 roots being P1 and P2. Okay? Take a look. Yeah. So if this has not been, it doesn't look familiar to you, please let me know. Yeah. So this is the way we will, kind of my way of notation. Okay. Yeah. Second order polynomial, but the exponent is negative. It's a little tricky. We are more used to the kind of polynomial when the exponents are positive. But here, the exponent right here, 指数的部分, exponent, -1, -2. So please spend some time to make sure you are familiar with this notation. Okay, yeah. But otherwise, this is nothing but factorization. Simply the relation between roots and coefficients, 根与系数的关系 Yeah. So far so good. Yeah. Yeah. So in principle, we can do that. So where P1 and P2 are the 2 roots to this polynomial. So let's calculate P1, P2, shall we? Yeah. Right. So how do we calculate P1, P2? So basically, we have 1 minus z1 minus z equals 2. This is my notation. Let me just copy it. Yeah, so basically P1, 2 is, if we call this is A, this is B, this is C, then we can apply the formula. P1, P2 is basically 2A at the bottom, my reference V, plus or minus square root of B squared minus 4AC. Seriously, this is nothing but that. Yeah. It's nothing but that. Yeah? Okay, yeah. So equals to 2 times 1 minus B minus of minus 1 plus or minus B squared minus 4 minus, seriously, that's that. Yeah. This is nothing but applying this good old formula. Okay, yeah. High school math. So now we have the famous factor of 1 plus or minus square root of 5 divided by 2. The golden ratio. Some of you might notice this is that's P1 and P2, the 2 roots. Okay, seriously, this is what we need to go through. Okay, this one was in our derivation. And remember, why are we doing this? Please be reminded that we are trying to calculate the impulse response. Okay, but somehow I suggest, or the textbook suggests, that we go through this factorization, 因式分解. We go through this factorization. That's a middle step, intermediate step right here. Okay, so let's follow this. So if you're okay to follow this, so far so good. Are we okay? Yeah, are we okay to follow this way of derivation? So this is a intermediate step, and then we have calculated both roots. then the next trick has a name. Okay, the next trick. I said this really is a trick, but if you prefer, it has a name. The trick is called partial fractional decomposition. Partial fractional decomposition. And what is that? So remember that this is h of z, right? B divided by a, that's h of z. And h of z, we have shown that h of z, now h of z, we have shown that it is 1 minus p1z inverse. There is a factorization in terms of the product of two terms. Now, this is the product expression. 乘以嘛, just product. This is a product way of expressing h of z, but it has another way, another expression. Okay, so it turns out that any bz divided by az in principle, if the bz's order is lower than that of a of z, b 的阶数 if bz's order is lower than a, if b's order is lower than a, and in this case, indeed, this is B. B is zero order, right? A is second order, right? So B's order is lower than that of A. If that's the case, then we can rewrite. You can always perform this fractional decomposition into 1 minus P1 Z inverse, and there's a coefficient A alpha K that has to be determined. Let's call it alpha 1 right here. Okay, and next is 1 minus P2 Z inverse, and there is also a corresponding coefficient alpha to be determined. Okay, and this the fact that we can always write this, we can always find alpha 1 and alpha 2 such that the identity holds. Okay, this fact, the fact that we can do this is called partial fractional decomposition. Okay, you can always do this. Unless, okay, there's an exception. Unless A has a multiple root. 如果 A 有重根的话, situation will become more complicated, slightly more complicated, but let's not worry about it for now. Because in this case, we don't have multiple root. The two roots are different, right? One plus or minus square root of 5. So the two roots are different. So we don't worry about the situation for now. With the multiple root that can make our story more complicated. That complicates our story, but let's not worry about it for now. Okay, but this is kind of the recommendation. Let's try to find. So let's just force the equality to hold, and then we attempt to find alpha 1 and alpha 2. Okay, where P1 and P2 have already been solved. We already know P1 and P2. P1 and P2 are these golden ratio. Okay, P1 and P2 are already known right here, but what's unknown, still unknown, is alpha 1 and alpha 2. So far, so good? So that's, again, the second intermediate step. One side, one step. Okay? All right, so let's follow the slide. This trick is called partial fractional decomposition. And if we are fortunate that AZ does not have any multiple roots and B's order is lower than that of A, then BZ divided by AZ can be further rewritten in the following form, where P's are the roots, which we have calculated, and the alpha coefficients need to be determined. So we'll show that in the next slide. Okay. Yeah. So now let's do this exercise, okay? So as I showed here, the exercise is how do we calculate alpha 1 and alpha 2 given P1 and P2. Yeah. And so let's do it. Okay, so I left one really blank page for you to use. But basically, let's work on the right. But basically, we have P1, P2 is already given, right? P1, P2, P1, P2. I've already calculated P1 and P2. Okay, so there are a few different ways. Okay, one possible way is to just keep playing with this expression. Okay, if the equality holds, then the bottom should be 1 minus P1z inverse. Let's put the two terms back together again. Put the two terms back together again. On top, what do we have? On top, we should have alpha 1 multiplied with that plus alpha 2 multiplied with that, right? Should I repeat? Yeah. I want you to take a look, right? So if we just keep playing with this expression, then going back to put these two terms together, then at the bottom, the denominator right here should be back in this expression, but on top, the numerator should equal to alpha 1 times 1 minus P2. I'm sorry, 2, the P2 right here, the inverse plus alpha 2, 1 minus P1 the inverse, which equals to that. Okay? So far, so good? Yeah. Now, this is one way. I'll show you another quicker way, but this is a more sort of naive, 比较天真 or naive. This is a nice word that we should all learn. 天真 naive. This is one naive way. The naive way. Naive. With two dots, okay? This is French. Yeah, it's a naive way, 天真的方法啊。The naive way is not bad. 不是要求啊，是天真。写好一点，天写成妖就不好妖真啊。The naive way is to do this, okay? But what's next? Any suggestion? What's next? In this naive way, because this is equality, right? So we can compare this expression with this expression. The bottom is already the same, but the top also needs to be the same, right? So we can say, okay, therefore from here we have two equations for alpha 1 and alpha 2. The first equation is the constant term alpha 1 plus alpha 2 must equal to 1, right? Yeah. So alpha 1 plus alpha 2 must equal to 1. And secondly, alpha plus minus of P2 plus alpha 2 plus minus of P1 must be equal to what? To 0, because on top right here, we don't have the Z inverse term. We don't have the Z inverse term, okay? So alpha 1, P1, no, P2. Is it P2? P2, right. Yeah. Plus alpha 2, P1 must be 0. So that's a naive way. We have two coefficients to determine, and then we come up with two equations. And you can solve the two variables with two equations. Okay, hopefully you can do that. Yeah, that's a naive way. In principle, it can be done. The P1 and P2 just look a bit ugly, with square root of 5, but in principle, this can be done. Okay. Yeah. So I said this is a naive way. Okay. So far, so good. Yeah. So if you're interested, you can work it out, okay? It will give you the solution. You can find alpha 1 and alpha 2 in this way. But the not naive way, the more professional way of finding alpha and alpha 2 is this other solution I'm going to suggest, okay? So let's try to see if there's a solution 2. So this is solution 1. And solution 2. In solution 2, ready? Are we ready? Yeah, so far so good? So there's another way, a slightly easier way. Okay, yeah. Solution 2 is to focus on this equality, okay? Focus on this equality. Let me use another color. Solution 2 is to focus on this equality right here. And then let's multiply both sides of the equation by a factor. Let's multiply, for example, let's multiply both sides with the factor of 1 minus P1Z inverse. So let's do this, okay? The equality should still hold, okay? So as a result, if you do that, then on the left we have this term. On the right, what do we have? On the right, we have alpha 1 plus what? Alpha 2, 1 minus P1Z inverse divided by, just multiply both sides with this factor. That's our recommendation. The equality should still hold. Okay? And the next step, is to let this term is big, and we want it to vanish. We want to make it disappear. Okay? All right, so that's the spirit. So next is to then consider Z equals to what? P1. Evaluate both sides by making this substitution. 代入, making this substitution, let Z be P1 and substitute. Then what do you see? Then what do we have? You see what's going on? Right? If we just evaluate both sides of the equation at Z equals to P1, then 1 minus P2 divided by P1, right? Z equals to P1, okay? Equals to alpha 1 plus what? Plus this big term right here, but it's 1 minus P1, Z equals to P1, and at the bottom is not important anymore. But for the sake of completeness, I finished writing, okay? So what do you see? Did you notice? Are you noticing what's going on? Beautiful. What's going on is right here, this term vanishes, right? We make the term vanish. 我们让它消失啊. We cancel the term. We make the term vanish by evaluating both sides at Z equals to exactly P1. Okay? So that's a kind of more professional or sophisticated way, This is a more sophisticated way of finding alpha 1. What is alpha 1? Because now, what do we have? Alpha 1 is equal to that. Everything is known. P2 is known, P1 is known. There's no unknown right here on the other side. Okay? So that's a trick. Yeah? Okay, people in the back, can you see? That's a trick, okay? I believe some of you might have learned this in engineering math or in the signal system, but this is a review, okay? Both are okay. I think both are fine, okay? Both are fine. But here, this is, so I say this is a more sophisticated way, finding alpha 1. So, let's just complete this. So alpha 1 is what? Alpha 1 is 1 divided by 1 minus P2 divided by P1 right here. Okay, that's a ratio. P2 is 1 minus square root of 5 divided by 2 divided by 1 plus square root of 5 divided by 2. Okay, I'm slightly running out of space, but you know what I mean. So alpha 1 is that. And so with some further bookkeeping all the factors, booking all the factors, you can figure out. Okay, use your blank space. 2 is now gone, so I would multiply top and bottom with 1 minus square root of 5. Okay, so this is 1 plus square root of 5 minus 1 minus square root of 5, and on top we have 1 plus square root of 5. And so the answer is what? Looks like my answer, at least, I will stop right here, okay? Yeah. Let me just stop right here. I have figured out that alpha 1 is that. Right? Not beautiful, yeah, it is a bit ugly, but I believe this is correct, okay? And it's both were find solution 1, solution 2, okay? And we are talking about, we're still in the middle of trying to find the impulse response, okay? We're stuck in the middle. This is the third intermediate step. Okay, so far so good. But yeah, just be patient. We can find alpha 1 and alpha 2. And in principle, you can also find alpha 2. So I will not repeat the process. I've done this at home. So you can also try it in your free time. Alpha 2, what do we have? Alpha 2 should be right here. Okay, so let me just copy everything to the left. So with a summary. Okay, so let's summarize. We have a system function. So let's summarize. We have a system function that's bz divided by a of z, which turns out we can perform partial fractional decomposition to write it as alpha 1 divided by 1 minus p1 z inverse plus alpha 2 divided by 1 minus p2, also z inverse, where P1, P2 is 1 plus or minus square root of 5 divided by 2. And we have figured out alpha 1 is that. Okay, let me take a look. Alpha 1 is that. We have as a result for alpha 1 and alpha 2. Okay, so I've done this at home. Alpha 2 turns out to be also in this form with 2 square. Yeah, so I'm trying to be careful. There's a minus sign, 1 minus square root of 5. Okay, yeah. So everything now is explicit. 每一样都已经写出来了. Everything is explicit. Yeah. We know all the factors, alpha 1, P1, alpha 2, and P2. But then what's next? The next is to understand that it turns out that each factor right here, these two factors have the same formulation, right? 长得蛮像, same formulation. Only coefficients are different. But then I suggest let's just force this sort of with a leap of faith. 信心跳跃一下嘛. With a leap of faith, let's just apply this identity. What is this identity about? It's just rewriting this term into an infinite series, into basically a power series. At least technically, this is my suggestion. Okay, technically, I suggest that let's rewrite this term which shows up in the partial fractional decomposition. That's that, right? And I'm missing a k, by the way. I'm missing a subscript. 下标忘了写啊. Please make a correction, okay? So right here, this is wrong. This should be alpha k right there, okay? Alpha k right here, alpha k also to the right, on the right-hand side of this identity, okay? So this is my suggestion. Rewrite this term into a power series. interpower series, and the beautiful. Please note that in this power series, all the coefficients showing up right here is pk, pk squared, pk third power, and so on. And why is that? So why could this be true? And that's because as long as this factor has an absolute value that's less than 1, then the identity holds. So this identity holds under a certain condition. This identity will hold if and only if, okay? If and only if the absolute value is greater, z is greater than this p right here. But when this happens, indeed, this equation, we have the identity, okay? This is kind of the opposite way, the reverse way of summing a geometric sequence, right? 几何级数等比级数求和 It's the opposite reverse way of, if you look on the right, we have alpha, that's just simply a constant. But in here, in the parenthesis, 在括弧里面 in the parenthesis, inside here, we have a geometric series. 几何级数嘛 you have a geometric series, p z inverse, p squared z minus 2, p third z minus third, right? So it's a geometric sequence. Yeah. So as long as the common ratio, 这个公比，对不对？ As long as the common ratio has an absolute value that's less than 1, then we can, that's a formula for the infinite sum. Okay? Here we're just using it in the opposite way. 我们是反过来用 That's a trick. Still, everything is trick right here. Okay? Yeah. We are still in the middle of trying to find the impulse response. But trust me, this is about the final step. So if you allow us, if you bear with me, if you just put aside your question for now, if you bear with me, then 搜一下 If you bear with me, then we can apply this. Right? The trick is to apply this following identity, which is an opposite way of summing of an infinite geometric series. Apply this identity, and now we apply this to our system. Okay? Apply this to our system, then what do we have? That's P1, P2, alpha 1, and alpha 2 with a minus sign. Okay? Yeah. So far, so good? So we can just directly apply this identity. And then this term becomes, that's the alpha part. That's alpha 1. Right? This is alpha 1, this is alpha 2. So far, so good? And then P1 to the nth power times z minus n. Okay? Plus, similarly, we have P2 to the n power times z minus n, and we just combine two terms. And we're almost done. Once you reach to this line, then the next is simply to notice this is h of z, now becoming a power series. 它是一个幂级数 power series 幂级数 It's a power series. Let me just introduce this term. I write it on the board. Power series. So now we have a power series h of z equals to summation of something, big thing, and from 0 to infinity, a big thing right here, and z to the minus n. So in general, anything with any function with this expression is called a power series. This is a power series, or in Chinese, it's called 幂级数. The power series expression of h of z with big thing inside right here. But what's the definition of z, h of z? The definition of h of z is summation hn z minus n, right? That's the very definition from the very beginning. H of z is defined as that. That's simply a definition, right? So now by comparing the last two lines, okay, please, if you go with me, comparing the last two lines, that's the very definition of h of z, now equals to this power series. And the only chance for the two of them to be equal, okay, the only chance for the two of them to be equal is for every coefficient right here. It has to, each coefficient should be the same in order for the equation to hold. Otherwise, there's no way to hold, okay? So that's just comparing the last two lines, okay? Now we have different expressions for the same function, so they ought to be, so every term has to be equal. And that's a kind of very basic property, essentially saying that you cannot have two different expressions. If two power series are equal, then every coefficient is equal. Okay, that is a very basic property in math, right? So therefore, now we have, by definition, h of z is the z transform of h of small h. But now, just after so many steps, we have h of z also equal to that. With inside we have the sum of two geometric sequences. Something like that. Therefore, h of n for every n must equal to that. 1 plus square root 5, that's the alpha part. P1, if you will, let's just explicitly write out P1 n power minus that times P2 to the n power. When n is greater than or equal to 0, because the summation index starts right here. Okay? And 0 when n is before time 0. Okay? H is an impulse response of a causal system right here. Okay? All right, so we're about on time. Okay, let's take a break of 10 minutes. So there are a lot of thoughts to digest. I agree. I acknowledge that. But let's come back and contemplate on our solution. Okay, when we come back, we contemplate on this solution. But let's take a break of 10 minutes.
算那个 magnitude 用傅立叶的话，是因为它是在那个单位元上面，但是 D transform 的话，它的 magnitude 就不会是一个线上，而是一个二维的那个。好，
不好意思，我现在忘了那个 midterm 的题目长什么样子，所以我可能没办法回答。而且现在马上要上课，好，明天再讨论好吗？或者待会下课可以讨论。好。Hello, yes. All right, so contemplation time. 凝视一下我们的答案。Let's contemplate what's going on right here. Okay, so we're still on the topic of Fibonacci series. Okay, so remember that we begin with this difference equation yn equals to the previous two terms. If you sum up the previous two terms, and as a difference equation, the system can receive an input. But then we are focusing on the impulse response, which means that we're interested in finding the system's response when it receives delta as its input. Okay. So this is our system H, and when it receives delta, I mean when it receives 1, a unit sample at time 0 and then nothing more. If the input is that, the output is what we're finding right now. Okay? The output is what we're finding right now. So, but basically, simply by plugging, this is our input. If you just plug this into this line of your computer code, this is one line of your computer code, right? And you run it iteratively while true. You do while true, n equals to n plus 1. Okay, yeah. 写程式, yeah, right? You just run this code iteratively, 递回的去算. You find out that the output y should be equal to 1 at time 0, then still equal to 1 at time 0, but then 1, 1, 2, 3, 5. Then we expect the output to be the Fibonacci sequence. Right? Yeah. So far so good? Is this clear? As a line of computer code, you don't even need to know about the transform. Just run the code. This is a result you should expect to get. Right? As a line, as a little program. And so on. Okay? And every term is an integer. So it's a bit funny if this is the first time. When I first encountered this result, I find it amazing. It's amazing that even though each term is an integer, but if you talk about a general expression for the nth term, if you consider general expression for the nth term, then the square root of 5 shows up, which is an irrational number. 这是无理数啊, right? So at least to myself, when I first encountered this result, I found it amazing. Okay? Contemplating on the result. Even though every term, and if you don't believe, let's try, okay? So if you don't believe this expression, let's try to see if it really is true. Is h of n really, is it really that? Is it really this big factor right here, p1 to the nth power minus? Are we really sure this is the result? Yeah. For n greater than or equal to 0, is it really the case? Right? So let's plug in a few numbers. Let's check. If n equals to 0, what do we have? When n equals to 0, right? When n equals to 0, seriously, we can check. 1 plus square root of 5, 2. Then on the left, we have h0 equals to that, and something to the 0th power, so that should be 1. Yeah. You can check a few terms. Yeah. Also this term, p2 to the 0th power. Yeah. So that's 1, that's 1. So we have h0 equals to 2 square root of 5 at the bottom, 1 minus square root of 5 minus 1 minus square root of 5. then indeed, lucky, it's really 1. So, yeah, so H0 is correct. Yeah. And H, how about n equals to 1? H1, seriously, we can check if it equals to this. And now P1, that's now the tough part comes in. But you know what I mean. We can really check. Yeah. So let's take a look. So now we have 4. It seems like we have 4 square root of 5 at the bottom, and on top we have 1 plus square root of 5 square minus 1 minus square root of 5 square. And what is that? What do we have? Still have 4 square root of 5 at the bottom, but on top we have 6 plus 2 square root of 5 minus 6 minus 2 square root of 5. And lucky, again, H1 is indeed still 1. And so on and so forth, okay? So if you don't believe yourself, you can do some numerical check of sanity to see if the equality that, yeah. So this really is an expression for Fibonacci series, okay? For Fibonacci sequences. Okay, so that can be checked. And what's next? So next we need to mention a few things, a few conditions for the equality to hold, for us to apply. Okay, so I mentioned that in general, when we have this formula, the kind of a reverse formula for geometric series. On the right, we're summing up a geometric sequence, P z minus 1, P squared z minus 2, P third, z minus third. That's a geometric sequence, okay? For the equality hold, we want the common ratio to have an absolute value that's less than 1. 公比嘛, the common ratio right here has z inside, so the common ratio, so we need to just, for the sake of completeness, we need to talk about this, okay? So a few points for us to mention, okay? The first, what we have is to obtain an expansion of h of z as a power series of z inverse, okay? Power series of z inverse. And equation 6, so on the previous page, this is equation 6. Okay? Equation 6 is here, let me just again write it. Here we have alpha 1, P1 to the nth power, plus alpha 2, P2 to the nth power. Okay? That's equation 6 on the previous page. Let me double check. This should be equation 6. Equation 6, right here. So take a look. Alpha 1, P1 n squared. Alpha 2, P2 n squared. Okay? So that's equation 6. But from here to here, the equality hold only if both these factors have absolute value of less than 1. Right? Otherwise, we cannot write this equality. Okay? We cannot go from here to here. This equality has for this equality to hold, there is a condition. Okay? There's a condition which requires that both this factor and that factor should have absolute value of less than 1. So that is to say, for this equality from there to here, for this equality to hold, we need to add a condition. Okay? The condition is for P1z inverse, that's a common ratio. Absolute value should be less than 1, and P2 here also has to be less than 1. Both of them need to hold. Both of them need to be true in order for us to proceed from this line to right here. Okay, equation 6, that's equation 6. Equation 6 holds only if both conditions are satisfied. All right? So how's it good? Yeah? Is it okay? And or equivalently, or in other word, okay? In other word, we need to have, if we just move z to the right-hand side, we need to have z, the equality hold only when z is greater than p1, and when z is also has to be also greater than p2 absolute value. Okay? In other words, z has to be greater than both of them. Or we can say z has to be greater than the bigger one of the two of them, okay? Which is 1 plus square root of 5 divided by 2. Okay? In order for this line, this very line, in order for us to go from there to here, we need to ensure that this is only true in a region where z, absolute value, is greater than this radius of 1 plus square root of 5 divided by 2. Okay? Yeah. So, and then again, let me mention that equation 6, then now the next point is about equation 7. Okay? In equation 7, that's the next one over here. That's equation 7. Okay? Equation 7 is just a simple definition, right? So I was saying that if we have two power series, we have two power series, and the equality hold over a region. And this is a very basic property in complex analysis. 复分析复变函数论. Okay? It's a very pretty basic property that when we have two power series, they may look different, but if you say the equality hold, then every coefficient should be equal. Okay, so you can plug in n equals to 0, n equals to 1, n equals to 2. H0 should equal to this, evaluated at n equals to 0. That's what we're doing right there. Okay, okay, so that's a very basic property. We cannot have two. We will never have two different looking power series that turns out to be the same. That's basically the idea. Okay? Or same principle can be applied to a polynomial too. 多项式也是这样. All right? So you have this, when this equality hold, and we know that it holds because this is simple definition, then the logical consequence is that each coefficient, hn, should be equal to this expression evaluated when with n right there. Okay, they should equal everywhere. All the coefficients they should equal. Yeah. So that's a kind of a subtle point that I think we also need to mention. We are comparing the coefficients on the two sides of equation 7, and each pair should be the same. Since we know the equality hold. Okay? Then what we get is now we get a general expression of h of n. Okay? So that's what's going on right here. And the next point is a terminology. Right? So we know that equation 6 holds, and that's part of our derivation, right? So this region where equation 6 holds, where we can apply equation 6, that region is called the region of convergence of this system. Okay? Of this particular system, this is a system. Of this particular system, now we can define its system function, and we interpret the equation in a causal manner. Then the region of convergence for our derivation to move on, we can define this region to be, it's called the region of convergence, where this power series converge back to the fractional expansion formulation. Okay? The region of convergence for this equality to hold. for this equality to hold, right? It holds only over this region, which we call ROC. Okay? The region of convergence of this system, which is outside the circle, okay? Z absolute value greater than that. So let's take a look. So often you can just we can also try to make a sketch of this region of convergence. So we say that h of z equals to yz divided by az and equal to 1 minus z inverse z minus 2. Okay? Over the region of z greater than this radius. And this is a subset of the complex on the complex plane, right? So this subset, this region on the complex plane, if you will, is on the z plane with real part horizontally and imaginary part vertically. So this is outside the circle, okay? Outside the circle, which center at the origin with a radius of 1 plus square root of 5 divided by 2, okay? Which is roughly what? Roughly 1.6 something. 1.6 something, okay? 1.6 something, okay? Yeah. So there's a radius, a circle of exactly that radius, and our region of convergence of this system function is outside. It's outside. Okay? It's outside, and just long story short, we have shown in the previous hour that if we consider h of z only in the outside, in this region of convergence, which is outside this circle, then we can be sure that indeed h of z can be expanded as the sum of two power series. Yeah. Sum of two power series. Sum of two power series. We can be sure that equality holds, long story short. Okay? Starting with the system function and then focusing on this region, then we are sure that h of z can be rewritten in this expression. Right? And from there we find h of n. Okay? From there we find h of n equals to exactly that. Okay? N greater than 0 or equal to 0. Okay? So that's long story short, and this region has a name called ROC, or not Republic of China, but region of convergence. Okay. And it's a causal system, right? H of n is defined. It's all 0 before time 0. Yeah. So far, so good. But the next is a note, okay? So note that this region of convergence, for this very system we have, for this exact system, the region of convergence does not include the unit circle. Why? The unit circle is inside this bigger circle, right? This radius is 1.6 something. It's larger than the unit circle. Okay? So the unit circle is inside, but the region of convergence is outside. Okay, for this this exact example, the unit circle is smaller. It's inside. That's the unit circle we have. Yeah, 1. Okay. So now here comes the question. Remember that we said in the previous meeting, we said, what is DTFT? Is there a relation between DTFT and Z transform, right? We say that, I share with you that DTFT is what? Is Z transform evaluated on the unit circle. I said that, right? Yeah. Remember that? DTFT is Z transform evaluated on the unit circle. Okay? H of Z, DTFT. When we have the impulse response, its Fourier transform is DTFT. Okay? It's defined as H of n e to the minus j omega n, summation over all n. Okay? That's the definition of DTFT. And we say that DTFT is Z transform evaluated on the unit circle, or is it just simply Z transform on the unit circle? And that's why we write DTFT as H, same H, but evaluated with Z equals to that. And that's on the unit circle. Z equals to that. This thing here is on the unit circle with omega can go from 0 to pi all the way to 2 pi and just repeatedly. The spectrum is periodic. Okay? But now here comes a kind of a dilemma, right? We say DTFT is Z transform evaluated on the unit circle. But in this case, we say Z transform is not defined on the unit circle because the region of convergence is outside this bigger circle. So how do we resolve this conflict? 这好像有点冲突在这边啊，有没有感觉到啊？这 what's going on, right? How do we kind of mitigate 就是缓冲啊，来调和 ？How do we resolve this conflict? Or is there really any conflict? Is there really any conflict? If the ROC now does not include the unit circle, that means what? That means the Z transform of H of n cannot be evaluated on the unit circle. That's the implication. It doesn't converge, right? It's outside. It's not in the region of convergence, right? So by definition, the Z transform of Fibonacci sequence does not converge on the unit circle. That's what we can conclude. Let me repeat this. Okay? The region of convergence does not include the unit circle. Therefore, now what we're talking about the Z transform of H of n. That's big H of Z. Okay? Equals to that. Yeah. So we are saying that this thing here does not, 不要写 limit 啊，也可以了，就 yeah. Note that this is an infinite sum, okay? So this infinite sum does not converge at Z equals to EJ omega. That's an implication. So really, there is, if you think about it, there's no conflict. Okay, we have a system. We know the response is going to be Fibonacci sequence, which has a general expression like that, and we can be sure that it does not converge on the unit circle. So that means what? That means the Fourier transform of Fibonacci sequence does not exist. We have a sequence 1, 1, 2, 3, 5, 6, 8, 13, 21, and so on. This as a signal is well defined in time domain. But let me emphasize that this signal does not have a spectrum. Because if you just try to evaluate the DTFT, it does not converge. DTFT is an infinite series. and it does not converge. The DTFT of Fibonacci sequence does not exist. That's the way we should understand. There's really no conflict. Yeah? We must acknowledge the fact that some signals simply do not have Fourier transform. Right? Yeah. So that's an important kind of message I want to deliver today. Right? Some signals do not have Fourier transform. Some signals do not have Fourier transform, right? So this is my conclusion. The kind of important message I want to make sure that we understand, okay? In other words, the Fourier transform of Fibonacci sequence does not exist, okay? So far so good? Yeah. Can we agree on that? Can we try to agree on this, right? So do you want to hear an even more tricky thing? It could be pretty misleading. This is important. Fourier transform of Fibonacci sequence really doesn't exist, but some people may argue, but take a look. This is h of z, right? And it's funny that if you write h of z in this expression, and you try to evaluate h of z on the unit circle, put a question mark, you can still come up with this idea. And everything looks fine. This is kind of a more tricky question. Yeah. My suggestion is that simply do not do this. Right? Do not do this. This is misleading. This could be misleading, right? So simply do not do this. If you talk about Fibonacci sequence, we here have an example where a signal does not have Fourier transform, no matter what. Okay, do not try this. That's my short answer. Think about this. This could be pretty confusing right here. That's a potential point of confusion. 这个是可能让造成混淆的地方。Please do not do this. Okay? All right, so now we can spend some time to talk about stability. Okay, yeah. So now we have the Fibonacci sequence as an example of an impulse response to a difference equation. And then in this difference equation, one of the roots of A of z is outside the unit circle. So A of z have two roots. One is right here. That's 1 plus square root of 5 divided by 2. And the other one is somewhere right here. The other root is 1 minus square root of 5 divided by 2. That's the other one. One inside the unit circle, the other one outside the unit circle. Okay? And so therefore, when we take the limit of n approach infinity, when we come back to this expression and we let n go to infinity, what happens? This one diverges, right? This term diverges and this term converges. Okay? One of the two terms diverges, the other converges. Okay? But the sum diverges. So limit of h of n when n approaches infinity does not converge. Okay? There's explosion. This one will explode. 会爆炸, yeah. 爆掉, yeah. So therefore, we say that the system is not stable in the bounded input, bounded output sense. Bounded input, bounded output. Okay, literally, what does that mean? So here, recall that impulse response is a response to delta function, right? Delta function is bounded. Here we have an example of receiving a bounded input, and actually, as a matter of fact, the input has only one term, one sample, one non-zero sample. It's certainly bounded. The input is bounded, but the output diverges. bounded input, unbounded output. So in that regard, the system is not stable. It receives just one tiny stimulus, a click, one sample. But then the output keeps growing. The output keeps growing, right? 1, 1, 2, 3, 5, 8, it keeps growing. So in this sense, we notice that the system is not stable in the bounded input, bounded output, meaning that even though it receives one bounded input, the output could be unbounded. Okay? And if you see this happen, the system is not stable. System is not stable, right? So let me just move on to the next point. So even though Fibonacci sequence is fun to study, right? It's historically important. But in principle, in DSP, we will avoid designing an LTI system that is unstable. We don't like it. We don't like our system to be unstable. Either to process your signal, right? You have a signal and somehow you want to design low pass and somehow say, sorry, the system is not stable, it's not good. Okay, so even though this is a funny example for us to study the solution to difference equations, it turns out that this kind of system is something, this design is bad. So later, when we come back from spring break, we start designing filters. Right? So one of the very basic requirements is to make sure that all our designs are stable. We don't want any unstable filter. Okay? So even though the sequence is fun to study, in principle, we avoid designing any system that is not BIBO stable. Right? And we learned that, therefore, when given a difference equation, if you're kind of your client, right? You ask somebody to design a filter, and you pay somebody to give you a difference equation, basically. When you design a filter, you pay somebody to give you a difference equation. So once you right? Once you receive a difference equation, the first thing you should check are the roots of AZ. Is any of them outside the unit circle? That's what you should do, seriously, to ensure stability in something that you pay for. Okay? So let me read this. Therefore, when given a difference equation, which might be somebody you employed, you pay somebody to give you a difference equation in the form of equation 1, linear constant coefficient difference equation. We want to check if any of the roots, denoted as PJ, any of the roots of A of Z is outside unit circle. Okay? Check that. If any one of them is outside, then this difference equation has a diverging impulse response as n approaches infinity, something like that. You'll have this impulse response will have a factor, a term like that, which diverges if any of the roots is outside. Okay, then you should ask them to 砍掉重叠, right? Please, you should discard that equation, right? Ask your client to spend more time and fix the problem. It's a problem. Okay, in principle, we don't want the difference equation to have a causal but diverging impulse response. It is unstable. We don't like it. Right? So far, so good. Yeah. That's kind of a lesson. That's a lesson that sometimes could happen also for your research. And the final point on this slide is a definition. It's simply a terminology. Okay? The root of AZ. So I'm making a cross. I mark the two roots with crosses. So we'll be in the semester. We'll keep using this notation. Okay. Wherever on the complex plane where AZ is 0, the roots of AZ is marked with crosses. 用打叉来标注啊。What are the crosses? And they have names. They are called the poles. They're called the poles or 极点, a poles, of the system. The root of A of Z is called the poles of a system. And they're often marked with crosses on the textbook and also as well as on my notes. Right? We'll be using this poles 极点. So the root to B of Z also have roots, and they are called the zeros. So just maybe I can erase this. So in general, what we have is yn equals to minus sign summation ak y previous samples, and we are making a linear combination of previous samples plus a linear combination of previous inputs, or no, where k runs from 0 to big N, right? Yeah. And then h of z, long story short, is bz divided by az, and both of them are polynomials of z inverse. We have b0 plus b1 z inverse plus something, please, b big N z minus n divided by 1, the leading coefficient is always 1, plus a1 z inverse plus blah blah plus a, the last term, a n z to the minus nth power. Okay, so that's our system function, and then you can factorize the denominator, okay, as basically 1 minus p1 z inverse, 1 minus p2 z inverse, and so on. And in general, it should have m roots. But on top, you can also do the same. B of z also have roots. B of z also has roots. And the roots of a of z, which are p1, p2, all the way to all these p things, are called the poles. p1, pm are called the poles. Whereas, let me just write down the, maybe on top. On top, you can also try to factorize, that can also be done. Factorizing the b of z, you may have 1 minus q1 z inverse times all the way to 1 minus the last root of b of z. And here, q1 to qn are called zeros, simply called the zeros. So these are the terminologies that we'll be using. Poles, zeros, the roots of az and b of z, respectively. 极点跟零点啊。Okay, yeah, so that's about stability and terminology. So we want all the poles to be inside the unit circle. Okay, so that's kind of a take-home message. Whenever you receive a linear difference equation, check whether all the poles are inside the unit circle. If they are, you are sure that the system can be implemented in a causal and stable manner. The system will be, when you implement the system in a causal manner, the system will be stable. Okay? There's nothing to worry about that. Now here comes kind of an exercise for us to take a look together, right? All right, so now let's take a look. This is an exercise. 多选题. We have 4 statements with the conditions, to see if we grasp the ideas that we are studying right today. Suppose that we have an LTI system with impulse response, small h, and system function, big H, which is the z transform of small h. And suppose that h of z can be written as b divided by a, where both are polynomials. And also we assume that the system is causal and stable. If the system is causal and stable in the bounded input, bounded output sense. Right? So let's see which of the following statements are true. First statement, all the poles of systems are inside the unit circle. Is it true? Oh, my answer is yes. Okay? All the poles should be inside the unit circle, given that we are told the system, now after ensuring that the system is stable, all the poles are inside the unit circle. Yeah. Second, the Fourier transform of Hn exists. Is it true? If all the poles are inside the unit circle, then the region of convergence includes the unit circle. The region of convergence for causal systems should be outside the largest circle, right? Outside the largest radius. But now all the poles are inside the unit circle. So the region of convergence, let me draw a picture. The second answer, my answer to the second statement is also true. If the system is stable to begin with, then all the poles, there might be, if the order of a filter is high, there might be multiple poles, but if all of them are inside the unit circle, here I'm drawing a lot of poles, but if all of them are inside the unit circle, then what is the region of convergence? Region of convergence is outside the largest radius, right? Region of convergence is outside largest radius, which might be this thing right here. That's the pole that is furthest apart, furthest from the origin. This might be the pole with the largest radius. And the region of convergence will be outside this circle. Here I'm probably, which includes the unit circle, right? So long story short, as a result, the region, the ROC includes the unit circle. That means the Fourier transform can be evaluated. That means that we can evaluate the transform on the unit circle, which is the Fourier transform. Okay? So there are different ways to talk about this, but yes, in this case, if the region of convergence is outside the largest radius, which turns out to include the unit circle, then, I'm just giving myself a hard time. Anyway, so then the Fourier transform of H of n exists. Okay, so my answer to the second is yes. Stable system has Fourier transform. The impulse response has a Fourier transform. Okay, and now moving on to the third point, limit. Does the impulse response approaches zero in time, when time goes to infinity? If all the poles now are inside the unit circle, if all the poles are inside the circle, can we conclude that the final value, some people say, when the final value, h of n, approaches zero in time as n approaches infinity, can we say that? Can we be sure? 增加你点头了 Why? Because take a look at here. Okay? My answer is also a yes. Because if you take a look, that we know that even without knowing exact value of alpha 1 and alpha 2, but the bottom line is that if all the poles here, P1, and in this case P1, P2, and more generally it could be P1, P2, P3, and so on, but if each of them has an absolute value of less than 1, then what happens? Then when n approaches infinity, they converge. Every term converges to 0. Therefore, the sum also converges to 0. That is, say, h of n converges to 0 as n approaches infinity. Okay, that's also a property for BIBO stable system. Okay, so my answer to the third point is also a yes. 3 strikes. Okay, the last one. H of z converges over the entire complex plane except at z equals to 0. Is it true? Is it true? If h of z is defined as summation hn z minus n, does it converge over the entire complex plane except at z equals to 0? At z equals to 0, apparently it doesn't converge, right? But how about elsewhere? Okay, does it converge everywhere except at z equals to 0? And of course, the answer is no. The answer is no, because there's a region of convergence. Okay? It converges only outside the largest circle right here. Okay? Inside the largest circle, this sequence, this power series, if you will, does not converge. Okay? Yeah. So true, 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 false. Right, that's my answer. Okay? Yeah. So that's about all I want to emphasize for today. We have one final slide. Okay, we have one final slide. Any concern, any comments on here? Is something unclear? Yeah. Is everything okay right here? Yeah. So a lot of information today. Yeah. But here is almost everything I want to say about difference equations. How do we find the solution? And once we find the solution, we found that we need to care about the roots, the location of the root to a of z. Okay, so that's something I want to emphasize. We want all the roots of a of z to be inside the unit circle for a system to be stable, right? So that the solution can be written in something like this, a sum of geometric series, where the common ratios, 这些公比, the common ratios are the poles. Okay, so there's one last slide before we leave. This is a tricky slide. It's a tricky slide. Okay, so take a look. I need some room here. So let me erase a few things. So this slide is about that when we write a difference equation, the more natural way is to let the time go forward. 时间要往前走. That's a more straightforward way to think about difference equation. But it turns out that you can also think of a difference equation by making the time to go backward. This is strange. So this is strange, okay? So, but this is one last slide I want to share with you. So the idea is go this, which is not recommended. I don't recommend doing this. But let's begin with still this equation, okay? Yn equals to y sum of 2 past samples plus any input that we receive. Yeah, as a one line of code or as an equation, mathematical equation. We say like any n, right? Any n being integer, right? But somehow, if this equation holds for any integer, how about we let n prime equals to what? Yeah. So n plus 2. How about, let's try this, yeah. If n prime is n plus 2, okay? So then we have y n prime. Okay? Y n prime is n plus 2 is equal to, now n prime is n plus 2. So now we are using this equation by plugging and by replacing n with n plus 2. Okay, yeah. So now we have n plus 2 minus 1, that's n plus 1, plus y, n plus 2 minus 2, right? So this is strange. It's really strange. Now x of n prime is n plus 2. Okay? Now we have that. And the next, now let's keep yn on this side of the equation and move everything to the left. Or, yeah, let's call left, yeah, you know what I mean. Then yn equals to y n plus 2 minus 1 n plus 1 minus x n plus 2. right? This is what I say. Now the time is going backwards, sort of. Yeah. Why? So if you consider this being one line of your computer code, and what we have is that an expression of y of n in terms of its future samples. Y of n can be expressed in terms of future sample. It ought to be equal to 2 samples later minus 1 sample later minus the input that we will receive 2 samples later. So if you take a look at this, is this wrong? The question is whether or not this is mathematically incorrect. Is something wrong here? Seriously, is something wrong here? Okay. Time is up. Okay. So when we come back after spring break, let's spend some more time to think about this. Okay. This last slide will not be tested. 这个期末中考不考这个，先不要考，先不要管这个最后这样啊。So the midterm will not test you on the last slide. But when we come back, let's spend more time on this slide. What's going on? Is it mathematically incorrect to say so? Yeah. Given the difference equation, given that the difference equation has to hold for all n, can we just jump a few steps and reach this conclusion that the current sample will depend on future sample? Something's wrong or nothing's wrong. Okay, so when we come back, let's bring this question back to the classroom. All right, so see you tomorrow, and we'll do a mock exam discussion. Thanks for being here. See you tomorrow.